Okay, so moving on with 7-1 here. It says triangle MNO is a 45, 45, 90 triangle with side length OM is 2, so that's all labeled on here. What are the 6 trig ratios for angle N with measure of theta? So they're having us look at this angle, so they want us to basically do sine theta, cosine theta, tangent theta, as well as cotangent theta, secant theta, and cosecant theta. And I always write them in that ratio, or sorry, in that order, just because that's the order of which ones are the like reciprocal functions. So just to recap that real quick. Where do we go? There we go. So each of these has a reciprocal function. You know, sine with cosecant is just opposite over hypotenuse versus hypotenuse over opposite. Cosine with secant, tangent with cotangent. So those reciprocal functions gives you kind of easy way. Once you find one function, you can then write the reciprocal one. Now they do tell us that these are 45, 45, 90, which does mean the two legs have to be equal. So those are both 2s. And if you remember the shortcut from the other day when we were talking about 45, 45, 90 triangles, you just take the leg and multiply by root 2. So this is going to be 2 root 2. So from here, we should be able to write all these ratios, no problem. So sine is opposite over hypotenuse. That's going to be 2 over 2 root 2. Now this is one that we are going to then need to simplify. We can't leave the root in the denominator. Now 2 over 2 is going to just cancel to be a 1. But we need this root 2 out of the denominator, so we go ahead and we rationalize that, multiply by root 2 over 2, and we get root 2 over 2. So that's going to be that one. Now, when you go to write cosecant, remember, instead of opposite over hypotenuse, it's going to be hypotenuse over opposite. So hypotenuse over opposite, sorry, was going to be the 2. That's 2 root 2 over 2. Reduce those, and it's just root 2. Now, you could flip this over, but when you flip it over, you're going to put that root 2 in the denominator. Then you're going to have to redo this step. So both ways do work, but it does make more sense in this case to just write it from the triangle. All right, cosine, adjacent over hypotenuse, is going to be the same exact ratio we just did because it's a 45, 45, 90. So we already know what it's going to simplify to, but we go ahead and write it out if we want to. It's going to be root 2 over 2. Secant then is hypotenuse over adjacent, and therefore that's going to be just exactly like this one. It's 2 root 2 over 2, which we know simplifies to just root 2. And then our last two are the easiest. Tangent of theta, or tangent of 45 degrees, is going to be 2 over 2, which is just 1. So same thing over here because it's going to be adjacent over hypotenuse. Same thing, going to just be 1. All right. So that's how you can take one of these special right triangles like the 45, 45, 90, or in a second here, the 30, 60, 90, and come up with all of the different ratios for it. So as you can imagine, this question is asking us to do then the same exact thing, but for the 30-degree angle that's on here, right? Because this is the 30 because it's opposite the short side. So they want us to do sine theta, cosine theta, tangent theta, and all of their reciprocal functions. So it's cosecant theta, secant theta, and cotangent theta. Boom, boom, boom. All right. So what do we need to know? We are told this side's 4. We double it to get the hypotenuse of 8. Remember that rule. If we take the short leg and you multiply it by root 3, you get the long leg. And these are all those shortcuts back from 8-2. So I went over them then. And so, yeah, all we have to do now is write our ratios just like we did before. So look at this to do sine. Opposite over hypotenuse is an easy one. 4 over 8 reduces to 1/2. Cosine, or sorry, let's go ahead and we'll do the reciprocal functions as we do them. So that's going to be 8 over 4. Also very easy. It's going to be 2. Okay. Cosine, adjacent over hypotenuse. So now we have 4 root 3 over 8. 4 over 8 you can reduce down to 2. So this is just root 3 over 2. So we've got our values there. Now when we go to do the secant, that's going to be hypotenuse over adjacent. So that's going to be 8 over 4 root 3. That does simplify to a 2 on top, but you still need to rationalize your denominator. So we're going to multiply it by root 3 over root 3. So we're going to get 2 root 3 up top and just a 3 on the bottom. And there we go. Tangent, opposite over adjacent, 4 over 4 root 3. So those are going to be just 1 over root 3. But same step, rationalize this denominator like we've done a bunch of times now to get root 3 over 3. And then the last one, adjacent over hypotenuse. That's actually a pretty easy one. So you have 4 root 3 over 4, which is just root 3. Okay, so you can come up with all those. As far as your calculator and things, you can actually check this to a degree. Like you can check all of these because these are programmed in your calculator. So like you could do sine of 30 and see that it's a half. And then recognize that, oh, if I flip that, yeah, 2 over 1 is 2. And same thing here. You could do cosine of 30. You get this, and you can verify that it's the same thing as the root that we got by typing it in. And you can see, yep, that does in fact match up. So you can check these to a certain degree. Now, obviously, this is going to be just the reciprocal of that, but what you have to keep in mind is when you flip it, you then have to rationalize the denominator. So you can certainly check these to a certain degree. All right. This one, little try it. Go ahead and pause it, see what you can do. I'll draw it and work it out as well. All right, so I drew the triangle. Instead of 45, 45, 90, the hypotenuse is 5 root 2. So if you divide the root 2 out of this, you're left with just 5 for the legs. Then they wanted sine and secant of the 45-degree angle, or either one, it doesn't matter. They're going to give you the same thing. So sine of this would be opposite over hypotenuse, like so. Rationalize the denominator, get it simplified. Secant is hypotenuse over adjacent. So 5 root 2 over 5. Boom, those cancel and it's just root 2. Okay, so again, just kind of becoming more familiar with these 6 trig ratios, as well as using your special right triangles to be able to come up with the different side lengths and so on. So that's kind of the key there with example 4. All right, so this says which trig ratios are reciprocals of each other. And this says an identity is an equation that's true for all values of the variable for which all expressions in the equation are defined. You've seen that there's some trig functions include ratios that are reciprocals. So as we've been doing these, we've been noticing, and we've already been talking about it, that there's ones that are definitely reciprocals of each other. So for example, sine of an angle we know is opposite over hypotenuse. And then to be related to that, secant of an, cosecant, my bad. Cosecant of theta, we had written earlier, is hypotenuse over opposite. So those are reciprocals of each other. So the way that you can write this, like the way you can actually write what they call an identity, where you can say something that's always true, is you can actually say that sine of theta is equal to 1 over cosecant theta. So that's actually a true identity, because this is equal to the reciprocal of cosecant. Now we can actually write all 3 combinations. So like we've noticed that cosine is actually the reciprocal of secant. So this would be a true identity. And lastly, tangent is the reciprocal of cotangent. And these all make sense because this is opposite over adjacent, whereas this is adjacent over opposite. So when you put this over 1, it would flip it and they'd be equal. Same thing here. This is adjacent over hypotenuse. That's hypotenuse over adjacent. So when you do the reciprocal, it'll invert it and flip it. So these are 3 true identities. These come up a ton in the trig pre-calc course, so these are good ones to kind of remember and understand. And obviously, we're going to see a little bit this year as well as kind of an intro. All right, so then the next piece here says, how are the trig ratios of the 2 non-right angles in a right triangle related to each other? So obviously, in the right triangle, you have the one right angle, that's 90 of your degrees. Then you have these 2 angles, which also have to add up to 90. And there'd be any combination. They could be like 45 and 45. They could be 30 and 60. They could be 20 and 70. Obviously, there's an infinite number of combinations of angles, decimals and stuff you could put in there. So they actually define these as they call them alpha and beta. So A and B, alpha, beta. We know those add up to 90. And they are complements of each other. So alpha is equal to 90 minus beta. So whatever this is, if it was 70 degrees, you'd subtract from 90 and you know alpha was 20, so on and so forth. So they're complementary to each other. It says compare your sine ratios. And if you look at these, when you do sine of A, and we saw this earlier as well, they say it's going to be ZX over YZ, so opposite over adjacent. Well, we've noticed that actually also matches if you do cosine of this angle over here. So sine of alpha and cosine of beta are the same exact ratio. In the same way that cosine of alpha and sine of beta are the same exact ratio as well. And so because of that, this is another identity. So you know how we talked about how there were various identities where you can say one is true to the other one. So yeah, this is another one, that cosine of alpha, sine of beta, as well as you could write the opposite of it. Sorry, it's right here. Sine of alpha, cosine of beta. Those are both true trig identities. And these have a special name as well. These are called cofunctions, and the equations are called cofunction identities. Okay. So yeah, so that shows us how they're related, and it shows that these are always going to be equivalent to each other. All right, so next little piece here says triangle DEF has a right angle. Cool. D is alpha, E is beta. All right, so I'm going to go ahead and draw this while we're getting into it. So they want our alpha and beta angles to be D and E. So D and E, which would make our right angle then F. Okay, so D is alpha and B is beta, or E is beta. Okay. Sine of alpha is 8 over 17. So sine of alpha, if we're looking at alpha, is 8 over 17. We'll go ahead and write those in. And cosine of alpha is 15 over 17. Perfect. So we actually know all the sides of that triangle. Great. Now this says find sine of beta and cosine of beta. So technically we don't need a picture to do this. I'm just kind of doing it to sort of show you how this all comes together. What we do know is sine of beta is going to match cosine of alpha. So it should match this one exactly. It should be 15 over 17. That's what our identities up here say. If you want to double check it, sine of beta, 15 over 17, does make total sense. Okay, and then same thing here. Cosine of beta should match sine of alpha, which is 8 over 17. And if we want to double check that, yep, adjacent over hypotenuse, it in fact does. So we don't need to draw this picture. I just did to kind of illustrate that these are definitely true. Like they work no matter what triangle, what right triangle you're working with. But technically, you should be able to do this problem without drawing any picture, just by simply realizing that this is equivalent to sine of alpha, and this is equivalent to cosine of alpha. Okay? And that's pretty much that. Now, the next piece says, what are the cofunction identities for tangent and cotangent? If you think about it, you know that when you're doing these, like let's go back, let's look at this triangle actually just to make it simple. If you did in this one, tangent of beta, you'd get 15 over 8. If you did cotangent of alpha, sorry, it's not an alpha. There we go, there's an alpha. Cotangent of alpha, you would do adjacent over opposite, 15 over 8. And you notice those match each other. I wrote cosine. My bad. Let's rephrase that again. So sorry. Cotangent of alpha. That looks terrible. Let's just get it all out here. So cotangent of alpha equals. So cotangent of alpha adjacent over opposite would be 15 over 8. Again, the point I'm trying to make is that those are going to equal each other. That's a cofunction identity. So we could say that tangent beta equals cotangent alpha, as well as you could say tangent alpha equals cotangent beta. Those are two other identities that are true, and therefore tangent and cotangent are cofunctions. Also, they didn't ask about it on this one, but if you understand that sine and cosine are cofunctions, that would mean that secant and cosecant are cofunctions as well, which is why they have the co on them. Like sine and cosine are named that way because they're cofunctions. Tangent and cotangent are named because they're cofunctions. Secant and cosecant are cofunctions. So that's why those are named in a certain way. It probably makes more sense now as opposed to at the start when you saw just a bunch of random names. You didn't really see how they were paired. This is why they're named the way they're named. I believe that's it. Yep, that's why we're good today. And good luck on that assignment.